So, gonna do our penultimate lesson today. Okay, we're gonna have 12 lessons in this unit. And today we're gonna go over is a quick survey of chapter 31, which is all about polymers, okay? So we've learned some about polymers already, but we're gonna get some more terminology and some more chemistry in the notes today about them. So you may remember from this course earlier or some other course that you've had that what we mean by a polymer are very large molecules, but they're built with these repetitive units, right? And we call those monomers. So you take a lot of small molecules, you connect them together, you get a large molecule, and we call that a polymer. Now, one that we have made in the laboratory already this semester, early on, seems like forever ago, but it also seems like it was just yesterday, is polystyrene. And remember that we started with just styrene, liquid, and then we initiated the reaction in that experiment with a free radical initiator, and then we got a polystyrene pellet when it was all done. Good old days, right? Okay, so that type of polymer we call a chain growth polymer. We're going to look at two different ways of growing the polymer molecule. The first way, polystyrene is a typical example of it. It's called chain growth. And the reason why it's called chain growth is because you initiate a chain reaction where once you get it started, it just can't help but react. It's just, you create something that's so reactive, it will just keep adding monomers until it just can't anymore, most likely because it kind of falls out of solution and therefore isn't really in contact with monomer reactant anymore. So it's produced by chain reaction polymerization. And you can initiate it in three different ways. What we did in the laboratory early in the semester was with a free radical, but you can also do it with an acid catalyst or even an anion or base like catalyst, a nucleophile like catalyst. We'll look at those two mechanisms more today. The other interesting thing, or the other common thing about these chain growth polymer reactions is that they almost always, not always, but almost always will involve a alkene. And remember that the other way of saying that is if it's a vinyl group. Vinyl, remember, is where you have an R group that's attached to the carbon-carbon double bond. So let me just remind you what that means. So if we have a carbon-carbon double bond, and we have obviously 4 positions on that alkene. So if one of them is occupied by an R group, okay, this is what we call the vinyl. So if we consider that part of the alkene part of it as a substituent, that name we've been saying that's the vinyl substituent or a vinyl group. Okay, so that's what we mean by a vinyl monomer. Okay? All right, so again, it's a chain reaction. So once you create the intermediate, it just reacts with another monomer, and then that reacts with another monomer, and so on. Okay, that's the typical characterization of a chain growth polymer reaction. Okay, so as I said, we did that reaction early in the semester with a free radical, but today we're going to focus more on, well, how do you carry out a chain growth polymerization with some other catalyst like a positive ion, a carbocation, we're going to create a carbocation, or if we do it with a nucleophile, we create a carbanion that is the very reactive intermediate. Okay, so if we do it with a cation, then we have to have some sort of catalyst, and it usually is just an acid, just H+. H+ reacts with that alkene, as you can see in the diagram here. And when does this occur? Well, it all goes back to things where we learned even back in Organic 1. This will occur when we have something attached to the alkene that will stabilize the carbocation that is going to be present in the intermediate. And one way to do that is with an electron donating group. Okay? So any sort of electron donating group will stabilize the carbocation and therefore facilitate cationic chain growth polymerization. So it's effective only with vinyl monomers that contain an electron donating group, abbreviated as EDG. And the reason why this works is because that electron donating group is capable of stabilizing the chain carrying carbocation intermediate. So you can see that in the brackets here that our intermediate has got this positive charge. So anything about that electron donating group that will stabilize that positive charge is going to facilitate this type of polymerization reaction. It just repeats over and over again until you create the really large molecule. Okay. All right, so the other way to do it is with a negative charged ion, an anion. And so if it makes sense that an electron donating group will stabilize a carbocation and facilitate the cation chain growth polymerization, then an electron withdrawing group in the vinyl position will stabilize the carbanion and facilitate that mechanism of chain growth polymerization. So vinyl monomers with electron withdrawing groups, EWG, can be polymerized by anionic catalysis. In this case, the chain carrying step is a conjugate nucleophilic addition of an anion to the unsaturated monomer. Now, that's a lot of words, but I think it makes more sense if you look at what's going on here in the diagram. So a nucleophile will add to the carbon in the double bond, okay, which pushes its electrons onto the other carbon in the double bond, which creates a carbanion, which is very much a nucleophile. So that will happen again, and then again, and then again, and then again. So that's what we mean by it's a chain reaction. You start with a nucleophile. It doesn't have to be, it typically is, but it doesn't have to be something with a negative charge. But since this has this buildup of negative charge, this type of chain growth polymerization is facilitated when the substituent on the vinyl group is something that can kind of tamp that negative charge down a little bit. It can, through inductive effects or through resonance effects, can lessen the concentration of that negative charge, delocalize it a little bit, and therefore stabilize it. Okay, so what we want to do is, in this example question, we want to order these with respect to their expected reactivity toward cationic polymerization and explain your answer. Okay, so one way to think about this is we need to just think about attached to each one of these vinyl groups is something else. And we need to classify whether it's electron donating or electron withdrawing. Okay. So, for example, this right here, methyl group, that we've talked about this before. Alkyl groups are considered to be electron donating. That is an EDG, electron donating group. Okay? So the chlorine, that's a little bit kind of a toss-up, but it's electronegative. But it does have those lone pairs that it can, rotate into the mix to possibly be an electron donating group. But for now, I just want to call it electron withdrawing group because it's electronegative. EWG. And I'm going to say that's because it's electronegative. Okay, over here in parentheses, I could put something like alkyl. All alkyl groups are considered electron donating groups. Okay, so this one, that's a benzene ring. That's like a phenyl group, so, So we have that alternating double bond, single bond, double bond, single bond. And so if over here, I've got a positive charge, then that's going to be stabilized by, I'll change to like a green color here. So, this pair of electrons can move up and form a double bond there, and that would put the positive charge on this carbon, which that could move this double bond to here and put the positive charge on this carbon, which that could push the electrons here and put the positive charge there. So you can see this one has got lots of resonance, okay? And so I'm going to definitely call that one electron donating group because it will stabilize that carbocation mostly through the resonance forms. Lots of resonance forms when I have that phenyl group. Okay? And then this one, if I could just redraw it, it's an ester group. Okay? And these are typically electron withdrawing. Okay? And that's just, it's somewhat of a memorization thing. Because you have these highly electronegative elements in there, oxygens, it's typically electron withdrawing. Okay, so the most reactive is going to be the most electron donating, and then that has to do with the resonance. So that's why the one with the benzene ring is the most reactive. So if you wanted to just number these, then I could put, let me change colors again to kind of make this distinct. Do pink. So most reactive, expected reactivity towards cationic polymers. So I'll just maybe label this one as like 1. That's the most reactive. And then the methyl group, I'm going to label that one as 2 because it's still electron donating, but it's not, there's no resonance forms involved. It's just, you know, the inductive effect at work there with the methyl group. Okay. And then the electronegative character of this chlorine is going to make it electron withdrawing. So it's going to be 3 in the third place. Okay. And then this ester group is just more electron withdrawing. It's kind of a memorization thing, like I said. So we'll give that 4. So would I expect you to, you know, to be able to do that without more information on a test? No, but you know, it's a good practice problem. You'd have to know more about how electron withdrawing chlorine is versus like an ester group to really rank those two. All right, so let me clear all that. That's a big mess. Okay, so now we're going to talk about different ways that these monomers can organize themselves, particularly when you have multiple monomer types. That could lead to something we call copolymers, and the name kind of gives it away. That's where the polymer is made up of more than one monomer type. However, you got to distinguish that from, well, what if it's all the same monomer over and over and over again? Those we would call homopolymers. Those are made up of identical repeating units. And contrast that with what we just said. A copolymer is when you have 2 or more different monomers reacting together, polymerizing together. So you heard of saran wrap. You ever wonder what that was? Well, there you go. That's what it is. It's a polymer that's made of these 2 monomers. You got vinyl chloride and then something similar. So on one of the carbons, there's 2 chlorines instead of 1 chlorine and 1 hydrogen. And that's called vanillidene chloride. And so when you make a polymer out of those 2 monomers, you get saran wrap. So they can organize themselves in different ways. It can be random, or it can be perfectly alternating, where you have A, B, A, B. So it just depends. So the exact distribution of the monomer units depends on 2 things. The proportions. If you've got a lot of one monomer type and a little of the other monomer type, you would expect that, you know, you would see, relatively speaking, a lot of one monomer and very little of the other monomer incorporated into the polymer. But that's not the only factor. The other factor is just the reactivity. Some monomers might be more reactive than others. So you got to take both of those into account. We don't get into that in any detail in this lesson or even in the chapter. If you're interested, you'd have to do a little bit of research on that. But just recognize that the 2 monomer types can be organized randomly, or it could be specific, like a specific pattern, alternating. Okay, now there are other copolymer types that we want to introduce, and one of them is called a block copolymer, and that's where, as the name kind of implies, you get a lot of one monomer type connecting together, and then the other monomer type connects together, and then at some point, those two blocks connect. So it's almost like if you're making Legos, you know, making a building out of Legos, and you took a big stack of red Legos and a big stack of green Legos, and you connected them together. That would be a good example of a block copolymer. The different blocks of identical monomers alternate with each other. Okay? Or the other thing you could do is you could have a polymer backbone that's all one monomer type, but then branching off of it, you have another block of monomers. So graph copolymers are homopolymer branches of two different monomers grafted together. So the idea here is if you had like a monomer type that was maybe unsaturated, and you could react that unsaturated part with something else, you could incorporate, you know, a different string of monomer units into it. And we would call that a graft copolymer. So again, we don't get into much detail here. Really what I'm looking for is, can you recognize these different polymer types if you see it? Okay, and this isn't even in your notes, but this, I thought you might be interested in it, is that, okay, if you have different copolymers, what can you make? Well, we already talked about saran wrap, but if you take styrene, which you're familiar with, that's a lot of things are made of styrene, like polystyrene, food containers, styrofoam. But you can do other things if you can incorporate that into a copolymer. Tires, rubber articles, okay? And this comes out of your textbook, so I won't go over all of these, but you can look at your online textbook if you're interested. But that's the really, you know, people who are interested in polymer chemistry, they're interested in the properties of the final product and whatever it takes to get those properties. Hardness, malleability, you know, resistance to UV light or things like that. There's all kinds of properties that are desirable. Okay, so now let's do an example question of a copolymer. So we want to draw the structure of an alternating segment of butyl rubber, a copolymer of isoprene, which the IUPAC name for that would be 2-methyl-1,3-butadiene. So let's just go ahead and actually draw that. Okay, so first of all, the 1,3-butadiene, so there's 1, 2, 3, 4. So we have a double bond at 1 and 3. And then on carbon 2, we have a methyl group. Okay, and then we're reacting that with isobutylene. So isobutylene is 2-methyl propene. Okay, so propene would be like this. We got a double bond, and then there's the third carbon, so 1, 2, 3. And then on the second carbon there, we also have a methyl group. Using a cationic initiator. So here's the big thing you can do is if I have a cationic initiator, it's almost like I erase that one, oops, turn that into a single bond. And so now this one has 3 hydrogens on it. So these are all hydrogens. Okay, so now the positive charge is there. And remember, it's going to go there. We know that because that's the most stable carbocation. That's a tertiary carbocation. Okay, but the other thing that can happen, and particularly for the purpose of forming a polymer, is that this double bond can kind of hop over. Okay, so now I've got CH3 with the single bond there, and then there's a double bond there, the methyl group. And so now that positive charge has moved over to carbon 4. Okay, and we even saw this mechanism when we talked about the 1,4 additions with conjugated dienes, and that's what we started with, a conjugated diene. Okay? So now this other monomer can act as a nucleophile and react with that, and basically it just forms a, forms a bond between those two. That's why I drew the arrow like a very poorly drawn arrow. Let me try that again. We can change colors so we can kind of make it distinct. But if I form a bond between this carbon and this carbon, it connects them, okay? And then to cut to the chase, what I get here is I get a CH2, okay? And then a CH, and then a CH3. Oh no, that's not a CH. Sorry, got to erase that. And then we got the carbon-carbon double bond. That's a CH. Okay, and then that's a CH2. Okay, so this is carbon 1, 2, 3, 4. So this is carbon 1, 2, 3, 4. Okay, so I'll change colors just again so you can kind of see where things come from. So we'll call this carbon A, and this carbon B, and this carbon C, and that's just a methyl group. So then that's connected to carbon A, so that's a CH2, which is connected to a CH, which is carbon B. Okay. Nope, that's not a C. That's a, sorry, it's not an H. You got to fix that again. Again, I guess I haven't learned my lesson. I keep trying to draw these structures. And I'm going to bring it up here in just a second. But okay. So CH3, CH3, and just pick one of these to call it carbon C. And then that just repeats itself. Okay. And again, I don't expect you to draw these from scratch on a quiz or something like that. It would just be recognition knowledge again. Okay, but let me bring up a nicer drawing of that. Okay. So again, it might be worth it to just kind of label things. So this would be, so as I said, this is A, B, and C, or the other one is C, doesn't really matter. And then change colors. This is carbon 1, 2, 3, 4. Okay. 1, 2, 3, 4. A, B, C. Okay, if that helps. Okay, all right, so let me clear away all that mess. Okay, so that's one type of mechanism for growing a polymer, chain growth polymerization. But there's another way to do it, and we also have experience with this when we talked about polyester and polyamides. This was back at the end of Unit 2 and at the beginning of Unit 3 when we talked about polyamides. But the thing about that's different about step growth polymers is that you don't create an intermediate that's wildly reactive. Okay, you create something, an intermediate that could react, but it's not necessarily going to react. And you'll see that when we start giving you demonstrated examples or examples. So it's produced by reactions in which each bond in the polymer is formed independently. And it's typically a reaction between two different functional reactants. Okay, so for example, you got there the production of nylon 66. Okay, the reason why it's called nylon 66 is because each of the monomers has 6 carbons in it, right? This adipic acid is properly named hexane dioic acid. And then the diamine is also 6 carbon chain. So as you can see, what you do is you have a reaction that creates amide functional groups. Okay, so the nitrogen acts as a nucleophile, attacks the carbonyl, and you form the amide. Okay, and then the other thing is that water splits out the plus N number of water molecules because one hydrogen from the amine and this OH come together to form a water molecule. That's a condensation reaction. So in this case, it's two different reactants forming these amide linkages to extend a chain. But there is another way to do it. And that's in the next slide. You could do it with just one reactant that happens to have two functional groups on either end of the molecule. And you could even sort of artificially generate that if you have a ring that you can open up. And we've learned about these type of molecules just briefly before. We talked about esters and amides. If you have an ester that's within a ring, we call that a lactone. And if you have an amide that's within a ring, you call that a lactam. And so you can catalyze the opening of this one, caprolactam, and what you get is, as an intermediate product, you get this 6-aminohexanoic acid where you've got the amine on one side of the molecule, and you have the carboxylic acid on the other side of the molecule. So in a sense, it's still like an intramolecular reaction. But if we allow one unit to react with another unit, then it creates a chain. And we call that nylon 6. So instead of nylon 6,6, because you're working with two different reactants, we only need to have one number. In this case, just 6 carbons from the caprolactam. Okay, so alternatively prepared by polymerization of a single reactant with two different functional groups. Okay. All right, I think that's it. Yeah, so we'll go ahead and stop there. And you know, again, this is one of those chapters, chapter 31, where I'm not presenting nearly everything in the chapter, just kind of selectively picking out some topics. And so here are some recommended problems that you can try from the end of the chapter. And I also have an active chemistry problem set. We're not going to work on it today because I do need to cut out a little bit early to go do some lab prep for my Chem 1 lab this afternoon. But that will be available to you so you can do some more practice problems with that. Okay? All right. Thanks, everybody, for hanging in there. We'll call that good for today.